The subject of my talk today is a white noise process and stochastic semigroup. This is my joint work with Irina Nishenko. And the history of this work is following. I had a proposition to one of our participants today, to Yuri Minyalik, to consider some problem, but Yuri rejected it. Then Irina give the same proposition to her maybe bachelor student, and then it occurs that the question is more hard than it seems from the first point of view. And so I want to present to you the problem and its solution.
I'm sorry, this is something bad with noise.
Okay, hope now we can continue. Let me firstly describe for you discrete approximation of the white noise. Let xi I be a sequence of independent Bernoulli random variables. We suppose that xi I are centered. Then, due to the central limit theorem, one easily have that the distribution of the normalized sum goes to the standard normal distribution and the n tends to infinity. Moreover, it can be proved that if we take the finite set of functions f1, fm, which are continuous on the interval 0, 1, and organize such sums which are very similar to the Riemannian sum, but instead of 1 over n, we just write the normalization from the central limit theorem and multiply the value of the function at the appropriate point on the epsilon k. It occurs that the law of distribution of such a normalized vector again goes to the Gaussian distribution, where the matrix A has a very simple structure. It consists of the integrals from these functions. These integrals are nothing else than scalar product in L201. So from this point of view, one can say that Bernoulli noise approximate Gaussian white noise in L201. Let me recall you briefly what is Gaussian white noise in arbitrary Hilbert space. So let us suppose that H be a separable real Hilbert space with the inner product and norm, then the Gaussian white noise psi in H is a family of jointly Gaussian centered random variables psi H, which is linear with respect to H, and for all H, psi H has a centered Gaussian distribution with variance which is equal to square of the norm of H. Due to the polar identity, it is trivial to see that if we consider that covariance operator of the white noise is equal to identity operator. Let us emphasize that it occurs that and it was discovered maybe 80 years ago that moments and expectations of products of weak polynomials from Xi are calculated via Feynman diagrams. There are a lot of special combinatoric rules to calculate, for example, expectation of products of such variables Xi h in different powers, beginning with the Dynkin formula, then Feynman produced a more general case. Moreover, it was proved in the paper of Anastasia Hrabovets that a Feynman diagram can be defined for Bernoulli noise too. So for those sums which we discussed here and which we define to be a Bernoulli noise, we also can produce the analog of the Feynman diagrams, but with more, of course, with more edges, and it occurs that some edges disappears in the limit, yeah, and we get exactly a Feynman diagram for Gaussian noise. So let us ask, where does Bernoulli noise appear? And in this my talk, I want to propose you the following idea. Actually, it comes from the one of the possible construction of a ratia flow of coalescing Brownian motion. I think that we discussed a lot ratia flow of coalescing Brownian motion at this seminar, and it is not necessary to write and to recall its definition and even its construction. Just let me say that one of the possible ways of construction of ratia flow of coalescing Brownian motions is the following. We just start from the any integer point of the real line multiplied by 2, and then we take independent Brownian, independent symmetric random, simple symmetric random walk starting from every such point, and coalesce when they meet. Then when we make scaling, we get ratia flow. We get the family of coalescing Brownian motions which are independent up to the meeting and which are starting from every point of the real line. As I said, I don't write any formulas because we discussed the subject at our seminar so many times that I think that everybody knows what is it. The question is, what happened if we consider the same construction, but on the other structure than integers on the real line? So let us start with the Ehrenfest model, because what is Ehrenfest model? We will see further that Ehrenfest model can be considered as a simple random walk, but on the hypercube. And then the natural question arises. If we suppose that we have a family of such simple random walks which coalesce on the meeting on the hypercube, and then take the dimension of the hypercube to the infinity, what we will get, and where we will get some limit if it exists. My purpose today is to give the answer to this question, but let us proceed step by step. Let us start with the Ehrenfest model, and this example was considered in the paper of Yuri Minyanik. Gaussian noise related to Reinforced model. Here is the paper. And suppose, and this is a description. Suppose that x be a set minus 1, 1 in power n. N is fixed number. And consider a random walk on x. Random walk is very simple. At every step, we randomly choose k coordinates and change its values on the opposite. It is a very slight generalization of the original Paul and Tatiana Ehrenfest model, where they discussed a case when we, for one step, we choose only one. Yeah? Here, you propose to choose k coordinates. Suppose that the initial point consists. Now, let us think what we will have if n tends to infinity. What happened with this random walk? How it must be appropriately scaling? This is the first question. Scale it. And the second is where we have to consider this limit. Because in contrast with the integer numbers, when we take n to the limit, it looks from the first point of view that we have no appropriate, even appropriate space. And the idea is the following. Let us start not from the fixed deterministic point in x, but let us start that initial point consists of independent Bernoulli variables. So initially, the distribution of our random walk is just a sequence, finite sequence of independent Bernoulli variables. Then it occurs that for every n, epsilon also consists of independent Bernoulli variables. It is interesting fact. It is due to the structure of Bernoulli variables because their distribution is symmetric. And it was proved by Urey that under n tends to infinity and k over n tends to some alpha, it is important, alpha is from 0 to 1, then the sequence, this Bernoulli noises, let me recall you, that for every n small, we have Bernoulli noise which we can construct as we have seen previously. This sequence weakly converts to the sequence of Gaussian white noises, psi n, in L201, which is moreover, which occurs to be Ornstein-Uhlenbeck process. Of course, it is with discrete time, so maybe it will be more formally and more precisely good to say that it is the solution to autoregression equation with one step, but we understand that it is the discrete analog of Ornstein-Uhlenbeck process. Here is
Andrey, I'm sorry,
yeah.
what is En?
En, where is epsilon?
En converges to the sequence of Gaussian white noises.
The sequence epsilon n. Epsilon. Here is
Epsilon n.
The same epsilon. So it is the same epsilon like here, here. Yeah. So for every n small, it again consists of independent Bernoulli sequence. One can consider Bernoulli noise based on this epsilon n, and it occurs that sequence of these Bernoulli noises converge weakly to the sequence of Gaussian white noises which satisfy such regression equation.
I don't understand what is epsilon n. What is the formula for this Bernoulli? So which could you please repeat one more time?
Okay, yes, it is very interesting part. So you see, we start from this random variable, yeah?
Yes.
Okay. Using this random, one
Integral
can
sums.
yes, the following sums. So one can say that if we have finite sequence of Bernoulli noise, Bernoulli
So
independent.
we have convergence for finite dimensional vectors.
Yes.
Okay.
On every function, but you see, since Gaussian white noise has covariance equal to 1, it is not a random element. So all what we need just to check a convergence of finite dimensional distributions. Yeah.
Okay. So we have convergence of finite, yes, of finite dimensional distributions. Thanks.
Exactly. But also, and it is very important that we have this convergence not only for fixed n, but for company of n. So we have a sequence of Gaussian white noises. You see, this is when n capital tends to infinity, we get psi 0, psi 1, and so on, which are Gaussian white noises in L2.
So you have a sequence like one-dimensional, two-dimensional, three-dimensional.
No.
No?
For every fixed n, this sequence lives in Rn capital. And then we organize Bernoulli noise from this sequence. And when n capital tends to infinity, this epsilon 0 tends to psi 0, which is Gaussian white noise. When we put here epsilon 1, the same happened. Epsilon 2, the same happened. We get psi 2, psi 3, and so on. We have a sequence of white noises.
And psi 2, what is the dimensionality of this?
Again, it is infinitely dimensional. All these white noises live in L201.
Okay, I see. Thanks.
So this is the idea. You remember, the main question was, what happened when we consider this initial space, this one, and n tends to infinity? What happened with the sequences which of random variables which lives here? And the idea is let us consider Gaussian white noise related to it via central limit theorem. So we see that if we have just one random walk on the Ehrenfest hypercube and consider the case when dimension of this hypercube goes to infinity, then under appropriate scaling, here is it, we get the sequence of Gaussian white noises in L201 such that they organize it as Ornstein-Uhlenbeck process. They solve this autoregression equation. So the random walk is corresponding to Ornstein-Uhlenbeck process process dimension, the Bernoulli independent variables form it is exactly uniform distribution of the hypercube. It is easy to see that for Ehrenfest model it is stationary distribution. Yeah. So you are right. We get a stationary process, of course. So the question is, what happens if we have the family of coalescing random walks in Ehrenfest model when n tends to infinity? So since Ehrenfest hypercube has a very nice and simple structure, one can consider it not only one random walk, but a family of random walks, and one can say, okay, let they be independent up to the moment of the meeting, then go together. Yeah, it is very easy to construct such family. But what happened with this family when n tends to infinity? So I insist that we get the family of coalescent white noise processes, and coalescence will be regulated by the stochastic semigroup of random operators. This is the answer. And of course, I have to define what does it mean coalescent white noises and so on. It is not the same that coalescing Wiener process, for example. So we will see the answer step by step. So let us start from the example of the white noise processes. To do that, we need a more general definition of white noise with arbitrary covariance operator and mean. So suppose that M be an element of H and S be a continuous linear operator in H. Definition. Gaussian white noise in H with the mean M and covariance operator S is a family of jointly Gaussian random variables eta H, such that it is linear with respect to H, and such that eta H has Gaussian distribution with such variance and such mean. Oh, sorry for that. Here is variance. It must be written here. Of course, S is not arbitrary operator. It must be self-adjoint and must be non-negative. Yeah. Example: generalization of the Ornstein-Uhlenbeck process. Let eta n be a sequence of independent white noises in H, independent. Qn be a sequence of bounded linear operators in H such that the norm of any Qn is less than 1, non greater than 1. Now put psi 0 equal to eta 0, and then psi n plus 1 equal qn psi n plus, here we have this, e minus qn with star in 1/2 power eta n plus 1. Here the multiplication of the operator on white noise is defined very easy. For example, if we define operator R acting on psi, then what happened? We just say that by definition is equal to psi acting on R star u. Yeah, it is usual practice. Also, we need to understand that this requirement, norm of Qn, is less than 1, give us possibility to consider such square root. It is now well defined, so it is a well-defined formula, and one can easily see that psi n plus 1 is again white noise. with the identity covariance. So it can be checked by induction. But let me let me say to you the following. If Qn is an orthogonal projection onto subspace N, then Xn and Xn plus 1 will coincide on Ln plus 1. So you see, if we take these operators Qn in some special way, we can guarantee some stabilization of our sequence on subspaces and so on. And we will heavily exploit this in the future. To construct the Ornstein-Uhlenbeck process of white noises with the continuous time, consider the semigroup of operators. Let us start with the deterministic family of commuting bounded self-adjoint operators in H. Suppose it is JST, which satisfies the evolutionary property. So, as usual, JSS equal to identity operator, JT2 T1 T2, JT2 T3 equals JT1 T3. I can write this left-hand side in arbitrary order because we suppose that they are commuting. Suppose that also they have no which is less or equal than 1, then one can check the following theorem. There exists a white noise process in H such that for all S and T, U and V and H, we have the following covariance via this semigroup JST. To prove it, we just have to use one of the possible way, of course, of proof is the following. Since JST is a family of commuting self-adjoint operators, it has isometric representation as a family of multiplication operators on some functions JST in some space in 2x, some measured space, where kappa is finite measure. For fixed, excuse me, S1 and or for fixed X, excuse me, fixed X small, for fixed X small, the function gamma is non-negative definite, and one can check this using the semigroup property. Then consider the finite number of time moments. Take again Xi1 and eta k to be independent standard normal variables, and define such normal variables which satisfy such condition. Xi k plus 1 is just JSK sk plus 1 Xi k plus those equations. And it occurs due to the semigroup property. We have to use it here. One can check that gamma is a covariance. That really it exists. Yeah, that such that one can check that gamma is a covariance. Then let me recall you it was for any x. Then it is easy that we can get our construction from this relation because we have isometric representation of H as L2 X8.
Excuse me.
Yes.
And we have this representation with J small as a consequence of some general form of the spectral theorem, right?
Yes, yes, exactly. I said. By the way, I think that I don't know exactly, but at least one of the person who firstly paid attention possibility of the spectral representation of family of a commutative self-adjoint operator was Yuri Makarovich Brzezinski. At least you can find such theorem in his book, devoted to the expansion on generalized eigenvectors. So we get this theorem, and we will say that this process is called by Stecker-Beck white noise process based on the semigroup JST. Let me show you some examples. Examples. If H is equal to 0, 1, consider F, which is simply a positive valued measurable function. And JST is a multiplication of the function JST small, which is like this, which is 1 if t is less than f, and 0 if t is greater than f. Yeah. Then also suppose that JSS is equal to 1. Yeah. Then there exists a white noise based on JST. And if fx is absolute value of logarithm x, then the process eta t, which is a product of our white noise with indicator of 0, 1, this process will be a usual Steinway-Beck process with a usual covariance. Yeah? But of course, if we take here some other function, the answer will be different and we get different processes. So this is generalized Steinway-Beck process. It doesn't mean that for any vector from H, when we get such a scalar product, we get usual Steinway-Beck process. No. So based on semigroup JST, one can construct coalescent white noise. Let me discuss it. Suppose that phi is a function which is acting from H to H, multiply on H to R, is a covariance function of the two white noises. So it is a bilinear function. Of course, it can be, for example, equal to 0 if they are independent. Yeah. Theorem. There exist two jointly Gaussian white noise processes such that here we see covariance. If we take II, the covariance is exactly the same as before. If we take different Xi1 and Xi2, the covariance is the following. Yes, we have this initial phi, and we have this term. Since then, one can see that firstly, Xi is a Gaussian white noise process. Secondly, if JST are projections, then such subspaces, you see that this FT is related to this. Yeah? Such subspaces increase because in the case we have semigroup of projections, the bigger the bigger this T is, then the smaller is the space on which we have a projection due to the evolutionary property. So the the orthogonal complement is bigger and bigger. It grows. So one can see that these two white noises began coincide on this subspace, and this subspace increases. And we will see examples when this subspace increases to infinity. From this point of view, this is explanation what I am calling by coalescing white noise processes. They are not coalesce like in case when we have two Brownian motions on the real line. When they meet, they coalesce. It is infinitely dimensional object. And one can say that, roughly speaking, some of their coordinates coalesce, yeah, which lives in this subspace, yeah, in this subspace FT. That's all what we can say. But further I will use not term coalescing, but term gluing of the white noise processes. The presented procedure allows to glue up the Ornstein-Uhlenbeck white noise process. Now we will use the stochastic semigroup of bounded self-adjoint random operators. I will propose a definition which is suitable for me. A mapping A, which acts from the probability space omega to the set of bounded linear operators, is called a bounded random operator if for any u A is a random AU is a random element in H. Definition. The family JST of bounded random operators in H is called by a stochastic semigroup if for all u from H, the function JSTU is continuous in probability, yeah, with respect to this S and T. Excuse me. Moreover, JSSU is equal to U with usual semigroup requirement. For all S and T and R non-negative, we have that JS plus R, T plus R is equidistributed with JST. And for arbitrary moments of the time, JS1, S2, and so on, JSN, Sn minus 1, Sn are independent. It is the usual requirement. We all face this requirement, for example, in definition of stochastic flows a lot of times. Let us consider very simple example. Let Wt be a standard one-dimensional linear process. Define JST as an operator of multiplication on this exponent. On this exponent, Wt minus Ws minus 1/2 of T minus S. This is it is trivial to check that it satisfies all the properties which were mentioned. And why I am giving such example, of course, there are a lot of other, but we all recognize in this expression the stochastic exponent, which is a solution to the simple stochastic differential equation. And it was proved by Anatoly Vladimir Skorokhod In his papers in 1983, 1984, where he introduced the notion of stochastic semigroup of even strong random operators with some more general subjects than bounded random operators. He proved that if such operator, which is expectation of JST, are inverted, then JST as a solution to linear stochastic differential equation with operator noise. So, from the point of view of this Skorokhov theorem, the example with stochastic exponent actually is only one example of the strong stochastic semigroup of operators under good conditions, because or other example is just generalization. Okay, let's take another stochastic differential equation. But if we forgot about this condition, we get a lot of different examples of stochastic semigroup, and I will need some other construction, which was proposed by me. It is a semigroup of finite dimensional projections. I proposed this construction in 2011. One can check related paper. Suppose that epsilon n is the orthonormal basis in H. Lambda n are positive numbers. Let for n, nu n be a Poissonian random measure on 0 plus infinity with intensity lambda. Suppose that nu n are independent. Then define the following numbers. Gamma st is 1 when nu n is equal to 0, and 0 when nu n is st is equal to 1. Finally, define JST, to be equal the following sum from n equal 1 to infinity, gamma n st multiply the tensor product En. This tensor product is one-dimensional orthogonal projection onto En. So since gamma has values either 0 or 1, one can check that for any fixed SNT, JST is a random projection. Now, it is also easy to check due to the definition that JST is a stochastic semigroup. It is interesting construction due to the following remark. Suppose that we have arbitrary stochastic semigroup of projections. Then it can be proved that it must have such structure as defined. So there are no any other stochastic semigroup of projections. Moreover, it can have an interesting structure. Why? Because always when we discuss this family of mappings, random mappings, which has a flow property, evolutionary property, we are keeping in mind starting point related to usual ordinary differential equation, deterministic differential equation, which give us the examples of very good families, evolutionary families of diffeomorphisms. Yeah. Also, when we say semigroup, that we always keep it in mind the deterministic examples too. What is deterministic example? This is a strongly continuous semigroup of operators in Banach space. Yeah, for example, heat semigroup in L2 or C on the real line. Yeah, and then one can think, okay, maybe we just add noise and do more or less the same. The next example will show you that there are no deterministic analog of the stochastic semigroup in some cases. Suppose that the lambda n are such that for any t which is greater than 0, the following series converge. Let me recall you that lambda n is intensity of the Poissonian measure on the n coordinates. So this equation, this inequality means, due to Borel-Cantelli lemma, that only at any positive moment of the time, only finite number of coordinates survive. So we have a semigroup consisting of the random finite dimensional projections, and it is continuous in probability. It is evidently to see that there are no such semigroup, for example, in finite dimensional Euclidean space deterministic, only the identity operator, only semigroup which consists of identity operators. Yeah. Now, let us consider the construction of coalescing white noises. Based on the stochastic semigroup of self-adjoint commuting random operators, one can construct the orthogonal and back process of white noises. The construction of conditional distribution under fixed JST omega is exactly the same as before. But I say under fixed JST omega. So for different omega, we get different deterministic semigroup JST omega. And then for every omega, it is white noise. So it's okay for fixed T, we get white noise value, but it is not Gaussian process, because for different omega we have different correlation. We just have a mixture. This is not a Gaussian process, but under fixed T we get the white noise process, usual Gaussian white noise process. Yeah. So now let's begin to gluing the white noise processes. The gluing is the idea of gluing now, I think, is very clear for you. Let us JST be additionally such JST is less than 1. For fixed JST omega defines the sequence of Gaussian white noise processes psi mt with covariance function of such way. Yeah. So you remember those phi. Those phi can be equal to 0. So I suppose that the 0 when we have this k not equal to j and is not 0 and is identity operator. So we have this one. We have this one. And then we define a mu j, the distribution of psi mt under fixed j, and finally define the distribution of the processes eta m together with JST in such a way that conditional distribution of eta under j is equal to mu j. Then for any t and m equal greater than 1, eta mt is a white noise in H. Then, if JST consists of projections, then eta M begin coincide on the growing subspaces of H. This is only one possible construction of gluing. Of course, one can now consider the different families of coordinates and try to make dependence between Poissonian process and so on. In says that we can glue up Poissonian process which drive our white noise coalescing process. Then in this way we get a family of not coalescing, I must say, but gluing white noise processes, and such family is a substitution of the Aratiev law or Ehrenfest model. Actually, that's all what I wanted to say today. Thank you for your attention. If somebody have questions or comments, it will be my pleasure to try to answer.
I have a question.
Mm-hmm.
My question is related to this paper of Warren Watanabe on spectra of noises.
Mm-hmm.
They construct a pairing of Harris flows.
Mm-hmm.
Can your model be used to do like this gluing of corresponding cylindrical Wiener processes to produce a...
After the talk of Jay Warren on this Quartz conference, you remember he discussed the noise and so. I also thought about this problem, and I think that answer will be positive, but only will be. Right now, I am not ready to speak about it, but I think that answer is positive. Actually, I think that this idea to not to describe the coalescence precisely, but go to the limit after scaling is very fruitful. And of course, I have different examples related to spin glass dynamics and so on, like in Telegram book. Is very fruitful and allows us to avoid different problems. For example, here, what was the point? When we discussed even two random walks on the Ehrenfest, in the Ehrenfest model, which are independent, then coalesce, move together, and when we began to discuss scaling, which leads us to the white noise process, it suddenly occurs that they are not Gaussian together. And this was initial point, because you see here we also get the processes of white noises which are not Gaussian together. They are just Gaussian under every T. So I think that the answer is positive. I already began to do some calculations, but I think that as I told, the answer will be positive. Yeah.
It's very interesting because it's very hard to do anything with those cylindrical processes for Harris flows directly.
Yeah, I think that, but still, I think that it is right way.
Thank you very much.
You're welcome.
I have a small question. I didn't quite get in which sense you have the evolutionary property for your family of white noises. Is it like weak or strong?
No, I have not any evolutionary property for it. I have evolutionary property for J, for the semigroup. That's all.
Yes.
For white noise,
but in
there
which
are no.
It is.
Yeah, there are no, like usual Steinberg process. We have no evolutionary property for it. Yeah? Even for one-dimensional Steinman process, we have no evolutionary property. We just have correlation, which is obtained from the stochastic dynamics. Here we get the same. The correlation is obtained from the dynamics, because JST, of course, one can take Skorokhod case and one can consider JST, which is generated by the stochastic differential equation, which is real stochastic exponent.
So I just thought that maybe this can be used, your construction can be used to construct like strong flows.
I think that actually no, because my idea is exactly following. You see, for me always this white noise recall me the cat from Alice in the Wonderland. There are no cat, but there is his smile. Yeah, and this is for white noise. But now we have even more ridiculous situation. We have no cat, we just have smile, and we have no space. Yeah, the space, this RNFS space disappears too. Yeah, so we have such a characteristic, and as Nikolai asked, it is very interesting to compare it with Cyrilson work and with J. Warren work, because of it is Heavy non-Hausian, yes?
Yeah, so this is like more the question about the noise.
Yes, yeah, exactly.
Okay.
Yeah. Other questions, please? Okay, if there are no other questions, I think that we have some break up to May 14, I think, yeah? Or something.
Let me check 1 second.
Oh, please check it.
Yeah, so the next talk is on May 13 by Maria Pilizerova.
Okay. I think it will be interesting about Poincaré-Bendixson and other stuff. Okay, very interesting. Okay, then thanks everybody and bye.
Okay, bye.
Thank you.
Bye.